In this video, we are going to discuss Gauss Law and its applications. Gauss Law, it is related to electrostatic or static electric field, where the charges are under rest. So we have certain charges Q here, or it could be here Q, Q1, Q2 like that, and here we can have some electric field. So how electric field is related to these charges, and here specifically we will define the flux of this electric field. Okay, so basically this is a statement for Gauss law. Total electric flux, that is a psi, through any closed surface is equal to total charge enclosed, this is important, by that surface. Okay, so mathematically what you can write, this total psi, okay, flux is defined by the surface integral, the closed surface, this is called closed surface integral of displacement density vector d dot ds elementary surface area. So this is called total flux, and this is equals to the charge q enclosed within this surface. So this is the statement, and now this d we can relate with electric field, and d equals to epsilon naught times E. Okay, epsilon naught, this is the media constant. Okay, and now here d is called displacement density vector. Density vector, whereas E is called electric field. And this displacement density vector is media independent. This is media independent. Okay, that is important thing. It's a media independent. Whereas E is depending on media, and this epsilon naught will be there. Like Coulomb's law, that E equals to Q upon 4 pi epsilon naught r square, and it is radial vectors. So this, you can see that this epsilon naught is there with the electric field, whereas in D there is no such media constant. It's independent of media constant. So this is a difference. So what we can do, we can also rewrite this thing as epsilon naught E dot ds, this closed surface integral, equals to charge enclosed. In other words, we can write this E dot ds for this closed surface okay, that is becoming this charge enclosed upon this epsilon naught. So we can use any of these two, but using these two we can find lots of applications. Now here it is important to understand, suppose if you have one charge here q, and if you consider one closed surface here, okay, and the electric field could be all the sides. Okay, it could be perpendicular, it may not be perpendicular, depending on the position of q. But whatever it is, this E dot ds, this dot product and their surface integral, and that will be equals to this small q upon epsilon naught. Okay, now instead of one charge, if I have more than one charge, then what I will do? So this is one q1, this is one q2, this is q3, these are three charges, and I have one closed surface like this. So here we are having certain electric fields. Okay, but again the E dot ds for this one, it will be same as total charge enclosed, means addition of this q1 plus q2 plus q3. This is total charge enclosed, and it is upon epsilon naught. Remember that if you have any other charge, it is outside. Suppose I have one charge q4 here, so it will not interfere anything. So this integral value will not depend on this q4. It is outside. So whatever charges are there inside this one, that will be the charge enclosed upon epsilon naught. That be very careful. So thus again be careful here. Suppose if we have two charge, one is plus q charge, other one is minus q charge, and if I enclose this thing by this surface, okay, in this case total electric field, total flux rather, E dot ds, this closed surface integral, that will be equals to plus q and minus q, means 0. Its algebraic summation is 0. The total surface integral for E equals to 0. Right? So sometimes we can express this electric field using Gauss law, all those things. Okay, so we can have some derivative form. This is the integral form, and we can have certain applications of this Gauss law. Before the applications, just I want to show you what is the differential form of this Gauss law. So using divergence theorem, what we can do? So E dot ds, this is the charge enclosed upon epsilon naught, and this one I can write rho times dB. Rho is the volume charge density. We will integrate our volume upon epsilon naught. So this is total charge. Now this surface integral, this closed surface integral, we can convert it to open this volume integral B, and that times divergence theorem we can use del dot E into dV. That will be same as rho dV upon epsilon naught. So if we compare these two, then del dot E, this one, this value should be rho upon epsilon naught. So this is the differential form of Gauss law. Okay. Now we will use Gauss law to find certain electric field for certain distributions. That is the most important one. And remember, you need to assign certain Gaussian surface so that you will get better results. Okay. Let us consider first example. It's a uniformly charged sphere of radius capital R, and total charge is Q. Okay. So this is all about, I have these three axes. This is X, Y and Z, and here we have one sphere. Okay, its center is here, its radius is capital R, and total charge is Q. So what is the charge density? Rho B. Total charge is Q, and total volume is 4 by 3 pi RQ. So this is the volume charge density. Okay, and this is uniform. This density is uniform everywhere. Now we can find out the electric field outside the sphere and inside the sphere. Okay, so first we will consider outside the sphere. Okay, so first consider outside the sphere. Means if I take a point here, this is a point, that is a distance r. At this point, what is the electric field? So to consider this thing, what I will do, we will consider one sphere passing through this element. Okay, and this sphere radius is small r. Their electric field is always radial, because this sphere center point is at origin, and we can assume that at every distance r the electric field is symmetrical, so it's a radial component. So this is the electric field directions, it's radial. So now we'll use Gauss law. I am considering that this r is more than capital R. Okay, so E dot ds, this closed line integral for this green one, it will be equals to charge enclosed within this surface, closed surface. So we have only this charge sphere, and total charge is q. So this is nothing but small q. That's all. Entire charge will be inside this sphere upon epsilon naught. Right? Now everywhere on this surface the electric field strength is same, constant. So its magnitude I will consider mod of E, and total surface will be 4 pi r square. So this total surface is 4 pi small r square. So that is equals to q upon epsilon naught. So what is the magnitude of E? So magnitude of E is becoming q upon 4 pi epsilon naught and r square. So electric field is always radial. So this is q upon 4 pi epsilon naught r square and r radial vector. And you can see that this expression is exactly same as if I have a point charge at this point, and that is only plus q. Because of that, also I will get the same result using Coulomb's law, q upon 4 pi epsilon naught r square. So this sphere, uniformly charged sphere, is behaving like a point charge located at origin. I hope this is clear. Now we will consider the point inside the sphere. Okay, so let us consider that. So this is the x direction, this is y, and this is z, and we have a sphere okay, and this radius is r, capital R. Now if I consider a distance r, small r, this is small r distance. At this distance I wish to find out electric field. So what I will do, I will consider a sphere around the origin with radius small r. So this is my Gaussian surface, Gauss surface, and this Gauss surface, it's a sphere, and there, and this electric field is suppose E at this point. So E dot ds, this is again equal to charge enclosed by this one. But remember that entire charge is not enclosed by this sphere. So whatever it is there within the sphere, that is the charge enclosed. So the volume charge density rho v is there. Now what is the volume, total volume? It's a uniform charge. So total volume is 4 pi 3 pi small r cube. So this is the total charge for this small sphere. Okay, and this total charge upon epsilon naught. This is the expression for total charge, and this is epsilon naught. Now if the magnitude everywhere on this sphere is constant, and that is mod of E, and total surface area ds, integration of ds, is 4 pi small r square. This is the surface area of this sphere. So that is equals to rho v times 4 by 3 pi r cube upon epsilon naught. So now this 4 cancel out, pi is also cancel out, and r square, this r will cancel out. So what is the E field? So E field will be simply rho v, and this is your 3 epsilon naught and times r, and it is a radial vector. It's okay. So these things we have got, this result is inside the sphere, and outside the sphere we got different results. Okay, so if we combine these two together, okay, then what you will get? Just try to understand this one. Now we will make this total, these two. Okay, this is the electric field. Now we can see that this electric field E is total Q four pi epsilon naught r square is a radial vector for r more than equals to capital R, and thus result we have got, it's rho v upon 3 epsilon naught times r, and it's r vector, and that is for r less than equal to capital R. Okay, so can I draw this electric field strength? So we can now draw the electric field strength over the distance. This is r, and this is suppose capital R, this is origin, and we wish to plot the magnitude of E. Okay, now we can see that at between this region, this is inside the sphere, and this is your outside the sphere. So inside the sphere, this is the expression. So it is proportional to r, so it's increasing. So you can see that this value is increasing till this radius r, and beyond that, this value is proportional to 1 upon r square, is reducing with the form 1 upon r square. Okay, so this equation is this one, and this equation is this one, and you can note that at capital R both will have the same things, right? Okay, let us move to the next problem. Infinite line charge. If I have an infinitely line charge, okay, it's a thin line, so this is infinite. If I consider coordinates, this is x, this is y, and this is vertical z. Okay, so from this axis at distance r, at this point, if we wish to find out electric field, then what we will do? So what I will do, I will consider a Gauss surface, and that surface I will consider one cylindrical shape, a small cylinders like this, with radius from the center, radius is r, and the length is small l or capital L, and this infinite line charge is having a charge density rho L. This is the charge per length, coulomb per meter. This is the unit, rho L, right? So within this Gaussian surface, so what is the total charge? So total charge will be only this one, that is enclosed by this one within this length. Okay, now here we can have some electric field, and this electric field is always radial, and every direction it is radial, that we are assuming. This is the electric field. So E dot ds by Gauss law, that is equals to the charge enclosed upon epsilon naught. Now here this electric field magnitude is E, and what is the surface area? This surface area. So 2 pi r into L. 2 pi r is this perimeter and length is L, this cylindrical surface area. Okay, this is a capital L. Now what is the charge enclosed? So within this capital L, what is the charge is there? So per length is rho L times this length L upon epsilon naught. So this L will cancel out. So electric field, its magnitude will be rho L upon 2 pi r epsilon naught. So you can see that this electric field, it is reducing with respect to 1 upon r. At r equals to 0, it is infinite, so it is going towards infinity. Very close to this one, electric field is very large, and if you move far away from this line, this field strength is decreasing, and decreasing is proportional to 1 upon r. It's okay. Next one, we will consider another interesting problem, that is a long cylinder with the charge density that is not uniform, that is rho equals to k into r. Okay, so this kind of problem is a little bit difficult to handle. So I have one cylinder, but it is long enough. Okay, so this is the axis for the cylinder, and if I consider the three axes, this is your x, y and z. Now at distance r, so this is your capital R, suppose this cylinder is having maximum radius is capital R. Now the charge, it is a solid cylinder, so this charge density is k times r, as so meaning is that toward the center point its charge is low, charge density is low. As it is moving towards the outside, it is proportional to r, it's increasing, right? Now at a certain distance r from here, this is small r, there I want to find out electric field. So what I will do, again very similar way, I will consider one cylinder, okay, with radius small r. Again the electric field, we will consider that it is always perpendicular to the surface. So E dot ds equal to total charge enclosed upon epsilon naught. Now what is the charge enclosed within these small cylinders? That you need to compute first. And left hand side is very easy. Left hand side is simply, what is this? It is a mod of E, magnitude of this one, and the surface area. This is your 2 pi r is your circumference, and length, this length is suppose L into L. This left side. So what about right side? For right side you need to integrate this charge density. Okay, so I need to consider this rho times dV upon epsilon naught. Here rho is given as k times r. So here we need to consider this dV in cylindrical coordinate system, and that is equals to r dr d phi and dz. So phi is the angle with the x-axis. So this angle is phi and height is z, and r is the radius. Okay, so this is the elemental volume in cylindrical coordinate system, r into dr d phi into dv. So that I need to replace here. Okay, so this is rho k into r, and dv I can replace r dr d phi and dz, and this is upon epsilon naught, but it should be triple integral, one for r, other for phi, and other for z. So z is the length, that is small l, and phi, integration of phi, it is independent of r, and total phi is 2 pi. So these two will be outside, so k is constant outside, and total dz is nothing but total length l, and total d phi is your 2 pi. And now this integral, what is the integral? Integral is r square, this r into r is r square, dr 0 to r, and this is by epsilon naught. Is it okay? I think we have got this one. So what is the expression for this one? This is r cube by 3. So can you see? So this E vector, its magnitude will be, so this is here coming as k into L into 2 pi, and this is your r cube by 3, and this is epsilon, and now this we need to divide by this 2 pi r into L. So L will cancel out, and 2 pi will cancel out. Okay, so what we will get ultimate results? So that we can write here, this electric field is becoming, this is 1 k, and this r cube by r is r square, proportional to r square, and this is 3 epsilon naught. And this electric field, if I consider electric field, it is radial. Right? Now I can note that here that it is proportional to r square. So as r is increasing, it is increasing like this way, this parabolically. But when r is more than capital R, then you can see that total charge will be there, and then again it will decrease with what 1 upon r square rate. Okay, so this is the inside and this is the outside. Okay, now let us consider another one. I have infinite plane, and it is a charged plane. This is an infinite plane. It's a very thin infinite plane. Okay, now from here at distance, and its charge density is sigma. and from here at normal to this one at distance r, at this point I want to find out magnitude of electric field. So what I'll do, I'll consider a Gaussian surface passing through this one, and I'll extend it to the opposite side and with the same length r, same distance r, this also r. So you can see that, so this is the portion it will cut in the plane, and if this area is A, this is also same area A, cross section area. So here electric field is outward, here also electric field is outward. Okay, so this E dot ds, total surface integral, will be charge enclosed upon epsilon naught. This is by Gauss law. Now what is the charge enclosed here within this area? Now charge density is rho. So obviously rho times of this A, this area is A. So what is the left side? Left side is magnitude of E. But this here, this magnitude of E, this area is A. And here in the below one, it's also same thing. So here also this magnitude of E into A. So this is the first term is for this surface area and this is for this surface area. Both the things we need to consider. Okay, that is equals to total charge enclosed, and charge is here. The sigma is charge density and area is A and upon epsilon naught. Now left side is becoming 2 times magnitude of E times A, that is equal to sigma into A upon epsilon naught. A will cancel out. So what is happening? E, magnitude of E, is sigma upon 2 epsilon naught. So electric field, its magnitude is becoming sigma upon 2 epsilon naught, and it is normal to this surface. And remember that it's an infinite plane, and it is not depending on the distance from this plane, because you can see there is no quantity r. So it's independent of small r, distance from this one, and that is because of infinite plane. But finite plane cannot have this kind of properties. Okay, but here it is constant. If it is close to, if you consider a point close to the surface, whatever field is there, if it is after 1 meter, you will be getting the same electric field. Okay, this value is sigma upon 2 epsilon naught, and it is perpendicular to these things, right? Now the final one, 2 infinitely plane, but they are parallel to each others, and they are having certain charge distributions. Okay, suppose I have one plate like this. This is one plate, and I have another plate which is again parallel to this one, and they are separated by a certain gap, that is d, and this separate charge is sigma, and this is suppose minus sigma. Okay, now we can use superposition principle. Try to understand, this is most important thing. Now consider that only this first plate is, this plate is present, second plate is absent, quite absent. Okay, so for this, what the electric field will get? So already I have said that electric field is perpendicular to this surface. So here electric field is, if it is positive, it is outward. This is the electric field, and that I will note as E plus for positive charge. This positive charge, positive sigma. And this side, it is this side, E plus. And remember that this electric field is independent of positions. If it is close to the surface or far away from this one, doesn't matter. So that means at this point it is also E plus. Beyond this plate, the D positions, no problem at all, because we have one plate, right side it is A plus outward, left side also it is outward, that's all, and everywhere we will be getting same electric field. Now for the second plate, now if I consider the second plate, this one, it's a negative one. So what is the electric field? Electric field is inward, and that is your E minus. Similarly, this one, so this is the right side of this plate, E minus, and left side of this plate, again it is inward. This is E minus, but its magnitude does not depend on positions. Similarly, here also I should get E minus. Now just I can combine all the fields. Suppose consider that both the plates are present. Then we can add these two together. Now what is happening? So inside this one, within this plate, so these two, they are having the same directions, they are additive. But here, E plus and E minus, these are opposite directions. Here also like that. E plus, E minus, opposite directions. And you can see that E plus and E minus, they are having the same magnitude because it depends on sigma upon 2 epsilon naught. Both are having the same sigma, one is positive, other one is negative, that's all. Okay, so these two will cancel. So outside this plate it is 0. This side also, this two will cancel. So only between these two plates we are having electric field, and that electric field is E plus plus E minus, and this value is sigma upon 2 epsilon naught. It is also sigma upon 2 epsilon naught, means sigma upon epsilon naught. So essentially what we are getting? We are getting an electric field only in these directions, from here to here. Here we are having electric field, and outside this plate there is no electric field, and this electric field strength E is sigma upon epsilon naught, and it is from this to this directions, positive to negative plate directions, and I can write normal directions. I hope it is clear. So if you have enjoyed this video, you can just press a like button. Thanks for watching. We will be discussing more problems. Thank you.